Last week, we hit a pretty good review of energy balances for open systems and closed systems. We simplified the general balance equation for whether it's steady state, adiabatic, closed constant pressure, closed constant volume. So hopefully the general balance equation for energy balances is set in pretty well. Today we're going to be talking about vaporization and phase changes, mostly just vaporization. So, the key thing that I like to emphasize, and everyone has heard this many times over again, is that thermodynamics, we're really teaching the system here. What we're doing is we're telling you guys how to unpack the data that is tabulated in the back of your book to solve real problems. The key thing to remember with thermodynamics also is that everything is a function of everything else. So we assume that an ideal gas, well it's true for an ideal gas, that its enthalpy and internal energy are only functions of temperature. It's not a function of pressure, right? Because they're so isolated and so, unconnected with other molecules that they only deal with themselves individually, which is what an ideal gas assumption is. So that holds true. But for everything else, every property changes if you change its density, if you change its volume, if you change its pressure, if you change its temperature. And that also holds true with vaporization. So the heat of vaporization, right, is the energy required to go from the liquid state to the vapor state. So with the delta notation, this is final minus initial. This is the enthalpy of a vapor minus the enthalpy of a liquid, and this is always going to be greater than 0. It takes energy to rip apart those molecules and disperse them into the gas phase. But this heat of vaporization is a function of temperature. So if I were a chemist or a chemical engineer working in a laboratory and I wanted to learn about a particular properties of some fluid, I'm not going to sit there and I'm not going to measure the heat of vaporization at every single temperature that is possible. What instead we're going to do is we're going to teach you guys a system of how we can go through the existing information that we already have. So in the back of your books, if you look at the heat capacity correlations, you'll see that there's a temperature range for which it is valid. That is the temperature range that someone has gone in the lab and actually measured those properties. So you have a range of temperatures for liquid heat capacities and vapor heat capacities. But when you go to the back of the book, you'll only see one tabulated value for the heat of vaporization. So the key thing is that when you're calculating a phase change, how much energy it takes, you have to go through that pathway. Right? It's kind of like a bridge to get through, get from the vapor state, from the liquid state to the vapor state. And we only know how difficult it is through some value that an individual has measured. So to highlight this approach that we're going to do, right, we're going to do it through an example. Now the example that we're going to work on is to heat up a pressurized liquid to a vapor. So we have a heating element that is inputting some rate of energy Q. The fluid we're working with is benzene. I'm going to just say it's 1 mole per second going into the system. Its pressure is 10 megapascals. And its temperature is 20 degrees C. And we're going to vaporize it. So this should obviously be a liquid. And we're going to vaporize it to 200 degrees C and 1 bar of pressure. So we have a lot of things going on here. We're changing the pressure, we're changing the temperature, and we're changing the phase. We have to account for every single one of these steps. Now, enthalpy we refer to as a state function, which means it doesn't matter how we get from this path to this path. The total amount of energy change is going to be exactly the same. So just because the process goes through a certain change in temperature and pressure doesn't mean we have to follow those rules. When we draw up a phase diagram, a PT phase diagram, This is our triple point. This is our critical point. Critical point is going to obviously be very important for this upcoming exam. We have which phase here at low temperatures and high pressures? Solid, liquid, vapor. So where we're going with this problem here, and it's kind of shadowed a little bit, is we're starting off at some high pressure and low temperature. So this is 10 megapascals and 20 degrees C here. And where are we headed to?
Low pressure, high temperature.
Low pressure, high temperature. Which phase?
Vapor.
So let's say somewhere up here. So we're going to a condition of 1 bar pressure and 200 degrees C. We don't know how the actual process is changing these conditions. Let's just assume it's going like that, maybe. We don't know. And that goes down to the design of the unit operation itself, how big the pipes are, what's the diameter, what's the rate of heat transfer. We don't care about any of that. Now, in our circumstances, right, this is the path that it may actually take. Which path should we take? We can take any path we want because it's a state function if we have access to unlimited data of all of the properties of the fluids. Which properties of the fluids are we most likely to have? So we have the critical point. That's typically well known for a lot of materials, which is not actually always true. Right? In our research, in our group, we do heavy hydrocarbon research, and a lot of compounds will thermally degrade before you reach the critical point. So you actually have to estimate what an apparent critical point may be. But for most things that we'll work with, we can know what the critical point is. Are we more likely to have the material properties of benzene at 10 megapascals or at 1 bar? Right. So the first thing we should probably do is to get ourselves down to 1 bar as soon as possible so that we have access to data. So we're going to have one step here. I'm going to call this delta H1. Now we are a liquid at 20 degrees at 1 bar of pressure. What's our next step?
You have to do phase transition.
Right, we got to get to the bubble point. So we're going to heat up the liquid till we reach the saturation point. I'm going to call this delta H2. What's the next step? So now we have a liquid of benzene at its saturation temperature. I'm going to call it T sat. Now what's the next step?
Vaporization or whatever.
Now we have to vaporize it. So I'm going to call that the heat of vaporization. Now we are vapor benzene at the saturation temperature at 1 bar pressure. And the final step is to
Heat the steam up, or heat the vapor.
heat it up. So I'm going to call that delta H3. So our total energy balance in this case right here is Q is going to be equal to N dot delta H. This is one of those circumstances where we can pull the molar or mass flow rate out and just use this delta notation. And this is going to be delta H1 plus delta H2 plus the heat of vaporization plus the final step. So delta H1 is depressurized liquid. Number 2 is to heat the liquid. Oops. Number 3 is to vaporize, obviously. And the final step is to heat the vapor. But recall, the practical reason why we're doing it in these steps is because we only have access to data at certain conditions. So if you are a company that, let's say, produces methanol, I guarantee that the databases at that company will have the properties of methanol for every conceivable temperature and pressure, because the engineers will use it on a daily basis. But the textbook, you have no idea what the instructor or the students are going to want to calculate properties on. So they're just going to present to you broad general information. So typically, we have access to the ideal gas heat capacity right? So those A, B, C, D correlations, that's the ideal gas properties. So you'll typically have the vapor ideal gas properties, because that's something you can almost calculate from molecular theory as well. Heat of vaporization, generally you only have the heat of vaporization at one pressure condition, which is the normal atmospheric pressure and temperature. Same thing with the heat capacity of liquids, right? Okay, so now it's just a matter of how do we actually calculate all of these steps. So in H1, this is a change in pressure enthalpy. In step 2, this is a change in temperature. Step 3 is a change in phase. So I could have constructed an arbitrarily different problem where we weren't vaporizing a fluid, we were instead crystallizing it or condensing it. So every phase change operation involves an enthalpy change. In this particular case, we're just vaporizing fluid. And the last step here is we're changing the temperature. We need to now use our tools that we learned last week when I was out of town, how to calculate the enthalpy change of pressure changes, temperature changes, and then for phase changes, we actually just look it up or measure it. We don't really have a really good way to do this. So let's get started on it. So step 1. For liquids and solids, we approximate the enthalpy of a pressure change using delta PV. The enthalpy is only a weak, the enthalpy is a weak function of pressure, but it's a very strong function of temperature. So when we're dealing with pressure changes, this is the form that we use to approximate the enthalpy. To use this in a practical scenario, we can make an assumption. We can say that if we pull the V hat, which is the specific volume, another way to think of this is the density. If we pull this out of our delta formulation here, what this is telling us is that the density of the fluid is not changing significantly as a function of pressure. If it was, we would have to integrate this function together. We would have to take the product of the pressure times by its density at every single step along the way, and you can imagine solving this numerically using tabulated data. What units do these need to be in? So for the Pascal, so for pressure, it would be easiest if we had this in pascals. And then for the specific volume, this should be meters cubed per what? Well, not kilogram in this particular problem because we're actually dealing with a molar flow rate. So we want to do this in terms of moles. So we want it to be specific volume, but in this case we want it to be the molar specific volume, just because everything else we're dealing with in this particular problem here is in moles. But if we had mass flow rates, then of course we would do this in mass flow rates. So for unit conversions, the density of benzene if we go through the unit conversion, for now, I have left it in units of kilomoles because otherwise I'd have to have a bunch of zeros and that's just not that fun to write. When we input all this information together, right, so all I did here was use the molecular weight and just did some unit conversion analysis, right? So this hopefully should be a straightforward step. We take our specific volume and we times it by our delta P. We're going from final state of 1 bar, which is defined as 10 to the 5 pascals, from 10 megapascals, which is 10 million pascals, or 10 to the 7. And we get that our delta H1 for depressurizing the liquid is equal to negative 8.8 times 10 to the 5 joules per kilomole, or minus 880 joules per mole. Intuitively, is that a big number? 880 joules per mole. That's a really small number. And we went all the way from 10 megapascals is effectively 100 atmospheres pressure. So pressurizing a liquid to 100 atmospheres only took us 880 joules per mole. This is basically why we neglect enthalpy changes with respect to pressure. It's there, but it's not a huge contribution. And we'll see how this contribution fits in relative to the other steps in our calculation process. So, actually, I don't need to do that. Let's do the next step. Step 2.
Sorry, can I ask, how do you use the density of benzene again?
So the density of benzene, so if you take the reciprocal of this, then that gives a specific volume, and then we just need to convert from kilograms to kilomoles. That's how we apply that unit there. Step number 2 is we are heating the liquid. So for this step here, we have to make an assumption of how we want to calculate this step. Strictly speaking, the heat capacity is defined, right? This is a defined unit that we have made up that allows us to do calculations more easily and to give us some physical intuition of properties of enthalpy. Is defined as the rate of change of enthalpy with respect to temperature. So if we were to plot out H versus T, the C sub P is the slope of it. The heat capacity is the slope. Now, if we want to calculate or solve for enthalpy, dH, so the integral of dH is equal to the integral of C sub P dt. So innately in all of our calculations, we should be never assuming that the heat capacity is constant. And that's why in a lot of the problems, you'll insert that polynomial function into this expression. Now, why was a polynomial function chosen? It's because it's very easy to integrate. Polynomials are trivial to integrate. But when it comes down to the sort of the science behind it or the physics behind it, the polynomial fit has no physical meaning or significance. It is only selected because it's easy to integrate. And actually, polynomial fits are generally a very bad idea for most calculations because they have secret sort of inflection points. And inflection points in science are extremely important, especially thermodynamics. So the polynomial fit here doesn't really convey the best fundamental information, but for conveying this point, it's good. Right? It's just a convenient function to integrate. Now, if we assume that the heat capacity is constant, we can pull it outside of the integral. Now, if we integrate dH, that just gives us delta H. If we integrate dt, that gives us delta T. And this is how we get to this point right here if we assume C sub P constant, if C sub P is constant. So in this particular example, we're going to assume a constant specific heat, but in order to mitigate the effects of this change or this effect, we're going to use it at an average temperature. So I'm going to say that the average temperature is 50 degrees C for this example. We are entering in the system at 20, and we're leaving at, oh, sorry, I'm leaving some pieces of information here. So the inlet temperature is 20 degrees C, and the outlet for this particular step, I'm jumping ahead and not sort of filling in all the gaps. For the liquid step, we're going to heat it to the saturation point. I forgot where we were going here. So step 1, we've depressurized the liquid. Step 2, we're heating it to the boiling point or the saturation temperature, which for benzene is 80 degrees C. Because we are assuming that we're not going to use a constant heat, we're assuming we're a constant heat capacity, to minimize the error, we're going to use it at an average temperature of the process, and 50 degrees is halfway in between our starting point and our finishing point. Now the numbers for this calculation here are delta H. This is the heat capacity at the average temperature. And that we get a value of delta H2 of 8.38 kilojoules per mole. This is about, what, 10 times larger? No, a lot, about 10 times larger. Yes, question?
The heat capacity at that temperature, is that tabulated or did you do a calculation there?
This one I calculated based on the coefficients provided in the back of the book.
Okay.
For that particular one.
Why do we need the E average there? We've never used that, right?
Well, so if we wanted to do this strictly the most accurately we could, we would have to integrate this expression here. And we would have to have some function that someone had fitted to get the heat capacity, and then we could integrate it in a mathematical expression. If we don't want to assume that, we want to say, let's say it's a constant heat capacity, which means we can use this really nice and convenient C sub P delta T formulation. But if we wanted to apply this one here, we would have to choose, okay, well, what temperature do we assume that the heat capacity is constant? We could assume the inlet conditions, 20 degrees. We could assume the saturation point, or we could assume somewhere in between. So if we assume that we take an average temperature, that kind of tries to correct for the offsetting errors. And that's why we chose to use the average temperature here. But oftentimes, you won't necessarily know what the outlet conditions are, so it's harder to use an average temperature. But in this particular problem here, we do know what the temperature range is. So we can use that approach to minimize our error. Okay, but look here. 8 kilojoules versus 0.8 kilojoules. A lot more energy goes into heating the liquid than it does depressurizing it. So pressure changes don't have a huge impact on enthalpy, and they have no impact on enthalpy for ideal gases as well. Now the next step. Step 3, vaporization. This was the easiest one. It's the easiest one because we made it the easiest step. In this case here, the heat of vaporization for benzene at T equals pressure equals 1 atmosphere, or T equals 80.1 degrees C. Right? P and T are linked in phase changes because of the Gibbs phase rule. This is equal to, and it's just tabulated, 30.77 kilojoules per mole. Yes?
So in this, there's a slight difference between an atmosphere and a bar, right?
Yes.
But we're not taking that into account because it's really small.
It depends on the data table. I use the two interchangeably. Oftentimes, tables will tabulate properties at 1 bar pressure, just because it's easier to implement into other calculations. But that very slight difference between atmospheres and bars is just kind of something I typically gloss over. It shouldn't have a huge impact on the calculations. But most data tables are actually at 1 bar pressure, just because it is that nice, clean, uniform 10 to the 5 pascals. And the last step, question, yes?
Is this, should it be negative because it's leaving the vapor, or are we putting it
Since
into
you're
the
doing a
vapor?
phase change.
This is actually positive.
Okay, so it's going into the vapor as we...
Yes, so the delta H of vaporization is equal to the enthalpy of the vapor minus the enthalpy of the liquid. So having this number be positive lets us know that the vapor has a higher enthalpy than the liquid does. And it makes intuitive sense as well, because when we're trying to boil the pot of water, we're putting a lot of energy into the system. So that energy is what's required to go from the liquid to the vapor phase. And so when we condense, it's going to be a negative value. Condensing would be liquid minus vapor, and this would be the negative of the heat of vaporization.
You actually answered it.
Okay. And the last step, step number 4, we are heating the vapor. And T average for this problem here is going to be 140, I think. Yeah, 140 degrees C, which is halfway in between 80 and 120. So our limits here are 80 to, 200. That'll get us to our final conditions. So our last step, the heat capacity of the vapor. And our delta T. And we have our final value there. Now, when we put everything together, the total rate of heat input to accomplish this task is the molar flow rate times by all of our specific enthalpy changes. Depressurizing the liquid, heating the liquid to its boiling point, boiling it, heating the vapor to the final set of conditions, and it will be 52.1 kilojoules per second. Should be our final answer. The least significant step of all of these was depressurizing the liquid. The most significant step was vaporizing. And the heating up were actually somewhat comparable. Now I want to spend a bit of time, well, first any questions on the procedure that we took here? The key thing that I want, okay, yeah, question.
Why is delta H vape equal to H vape minus H liquid?
That is a definition.
Definition of it.
Yep. So very, very clearly we could have reformulated everything saying, let's measure the heat of condensation instead. But since we define it as the heat of vaporization, it's defined as the vapor state minus the liquid state. And this is something that is tabulated that we have access to. So the whole reason why we did this entire process, I don't want it to seem completely arbitrary. We have the power, because enthalpy is a state function, to choose any path we wanted to. We could have instead heated the compressed liquid to above its critical point, depressurized the system as an ideal gas, and then cooled it back down and used that methodology.
Should have been 3 steps.
Might have been easier if we had access to the data. We would have to have access to the heat capacity as a function of temperature all the way from 20 degrees C to a temperature greater than its critical point. Those have got to be some pretty massive data tables, right? And how accurate can they measure those calculation values? Because this is a massive temperature change, and so you wouldn't ever want to assume a constant heat capacity under these conditions. You would definitely want to integrate them. The reason why we took this pathway here is because we took a pathway through steps that we had access to the data available to perform the calculations. That's why we chose this pathway. This is going to become extra important when we start to do reacting systems. So in non-reacting systems, you get to define your reference state. Generally speaking, you want to choose a reference state that's either the inlet conditions or the outlet conditions of a process, because that saves you some effort. Because in your energy balance, if you define your inlet conditions as a reference state, that means its enthalpy is equal to 0. So that means your energy balance simplifies to Q is equal to the enthalpy of the outlet. It makes it nice and easy. The other option is you could choose an arbitrary reference state. Let's just say, you know what, I'm going to calculate everything based on 25 degrees C in 1 atmosphere as my reference state. And then this would have a particular enthalpy, this would have a particular enthalpy, and you could apply your energy balance. But in reacting systems, we're going to take away that ability for you to choose your reference state. And it comes down to the same idea as this heat of vaporization. We only had access to the heat of vaporization at 1 bar or 1 atmosphere pressure because here on ground level of planet Earth, we have 1 bar of pressure. So if I'm going to go into the laboratory and measure heat of vaporization, I'm not going to make it difficult on myself. I'm just going to measure it at 1 atmosphere pressure. Same condition holds true on chemical reactions. We don't have a good way to estimate the energy accurately of chemical bonds without using very advanced quantum mechanics calculations, and even then there's some doubt on the accuracy of those. So instead we're going to measure them in the lab. So when we deal with chemical reactions, we need to have a reference state that we agree that everyone measures the energy of bonds at the same conditions. And that happens to be 25 degrees C and 1 bar. So if we want to know how much a CH bond, how much energy is stored in that bond compared to a CO bond, we all agree to measure those at the same conditions of temperature and pressure. And so when we do reacting systems, we're going to take away the ability to define a reference state. But in non-reacting systems, we can still choose a reference state. Now we have to go through pathways here. Pathways where we have known data. An additional thing I'd like to add and discuss is really reinforcing, let's use this one here. I want to reinforce the heat of vaporization as a function of temperature as a concept. So side by side, right now we have a PT phase diagram. I'm going to draw a different type of diagram. In this case, I'm going to draw an enthalpy temperature diagram for any arbitrary fluid. I'm going to have a critical point near the end of my x-axis, and let's just say that this is 20 degrees C, for example. This will hold true for every single fluid that we deal with. I'm going to put a marker right here, and I'm going to say that this is the enthalpy of a liquid at 20 degrees C. I'm going to put another marker up here, and we're going to call this the enthalpy of the vapor at 20 degrees C. On this graph, can you tell me what the heat of vaporization is? How would I know what the heat of vaporization is from this HT diagram?
What's the difference between the HV minus HL?
Correct. The heat of vaporization is this line, is the difference between these two right here. This is delta H of vaporization, but it's at 20 degrees C. What is a property of the critical point? That's really important. Well, it really defines the critical point. What is the difference between the liquid properties and the vapor properties at the critical point? There's no difference. So if I were to put 2 additional dots on this graph right here of the enthalpy at the critical point, what should they look like? They'd be the same point. Now where should I draw? Should I draw it down here?
No.
Here?
No, dude.
Up here?
Sure.
Probably somewhere up here. We're going to deconstruct why this is the case in just a moment. Let's forget about the phase changes. Let's just say we're talking about a gas at 20 degrees C, its properties. If I heat it up, I would expect its enthalpy to increase. By definition, actually, well, so the second law of thermodynamics tells us that the heat capacity has to be positive. So C sub P, the heat capacity, is d enthalpy dt. So the change in enthalpy as a function of temperature. That's the slope. Heat capacity has to be greater than 0. If heat capacity is less than 0, you actually violate the second law of thermodynamics. Now, the math required to demonstrate that is beyond the scope, but that's the truth. The second law tells us that heat capacity has to be positive under all circumstances. So what we can do is basically just say, let's just connect these 2 dots. This is assuming a constant heat capacity. In reality, it would kind of look like this. Right? It might look something about like that. But the straight line would be a constant heat capacity going from 20 degrees C to the critical point of whatever this fluid is. Yes, question?
Was that dot, you said the critical point?
This will be the critical point here. So this is the enthalpy at the critical point. So this is the enthalpy of the vapor, which is equal to the enthalpy of the liquid at the critical point. It's the same point for both the liquid and the vapor. Same as here. We have to connect these 2 points together. If we assume a constant heat capacity, the slope of this line is the heat capacity of the liquid. Now I'm going to try and draw this straight. That's pretty close. In reality, it wouldn't be like this. It would be actually some sort of a curved function that looks more like that. Let's take a second and think about what this plot is telling us. Let's look at the slopes first of all. Which slope has a steep, which line has a steeper slope? Vapor or liquid? Liquid. So this would tell us which should have a higher heat capacity, the vapor or the liquid? Liquid. Let's look at benzene. Is that true? So the heat capacity for the vapor, 115. Heat capacity for the liquid, 139. Now think about that from a physical perspective. Does that make sense? So the heat capacity of the gas in the back of the book is tabulated as the ideal gas heat capacity. There are no interactions whatsoever between the individual molecules. So if I give a molecule of benzene some energy, it has to either increase its translational velocity, how fast it's zipping around, what is the sort of intensity of the vibrations of the chemical bonds, how quickly it spins and rotates. Right? If I give benzene that energy, it has to store it somehow. It has to put it into some account or some piggy bank. And its options are vibrations, rotations, and translations. Now, if I take a liquid still has those same exact 3 modes of energy storage. Translations, rotations, and vibrations, but it also has an additional problem. It has to get along with all of its friends. Right? It can't just move around anywhere it wants to go to. It has to coordinate and communicate its position, its rotation, its vibrations with all of its nearest neighbor molecules. And that takes a little bit extra energy. And that's why the heat capacity of a liquid is always going to be higher than the heat capacity of a vapor. And we can see that in our graph right here. Now, what gives this graph a lot of power, when we know that the critical point is where everything kind of meets together and stays uniform, it tells us how the heat of vaporization is expected to change as a function of temperature. As I get closer and closer and closer to my critical point, my heat of vaporization starts to get smaller and smaller and smaller. So effectively what's happening is that as I'm heating up a liquid or as I'm heating up a vapor, the liquid, its energy is catching up to the vapor's energy. And when they meet and they cross, then they're exactly the same phase and they're the same state. They meet and there's no vaporization, heat of vaporization at the critical point, right? So that's what's going on. Now, when we're solving a particular problem, and I do a phase change operation, I have to remember that that phase change changes as a function of temperature, and the vaporization is bonded by this relationship here. Now, solid-liquid transitions, I don't know if they have exactly the same relationship, but we mostly care about vapor-liquid equilibrium expressions because distillation is by far the most common separation technique that chemical engineers do. So what I really want everyone to know is just the general concepts. Now, I don't expect everyone's going to have this completely crystallized and know how to solve all the problems after a week off of this material, right? Because we have the review on Wednesday and the exam on Friday. But what I really want to get accomplished in these past couple of days that we've been spending about energy balances is to really lock in the core concepts. Because once the core concepts are locked in, how we actually execute and solve this problem is not that big of a deal. We already solved this problem in the example today. Right? We could have chosen a completely different pathway to do our vaporization process. So in this particular instance, we had the heat of vaporization at 1 bar tabulated. So we used it. Let's say, for example, we want to know what the heat of vaporization is at some, let's say it's 200 degrees C. Right? You could definitely have liquid benzene at 200 degrees C, it just has to be a much higher pressure. If I wanted to estimate the heat of vaporization of benzene at 200 degrees C, I would have to go through a pathway where I know the heat of vaporization at some measured temperature and pressure conditions. So what I could do is I could take, my goal is to go from a saturated liquid to a saturated vapor at the same temperature and pressure. So it's kind of hard to draw on the phase diagram. But what I would do is I would first cool my high pressure liquid. I would depressurize my liquid. I would vaporize it at a condition where I know the heat of vaporization. I would heat the vapor up, repressurize the liquid, and I have done this simple step of going from a saturated liquid to a saturated vapor at a condition where I don't have the temperature and pressure measured, but I have to take this long path to get there.
But you gotta take the shorter one if you had known the information.
If we knew the information, boom, we could just pop right out. So there are correlations. So chapter 8.4 in the Felder book has a list of correlations that can accomplish this same task. So what they effectively do in those correlations is they rely on the notion that at the critical point the enthalpies are equivalent. So the correlations basically generalize these two fits and just say, let's assume everything behaves the same, and we'll just see, what is the ratio of the heat capacity of a vapor to a liquid for any standard fluid, and then they can use that information to sort of approximate what the heat of vaporization is as a function of temperature. So instead of me just listing out 9 or whatever correlations there are, just go to the book, check out that section. There are a list of correlations that can accomplish this task. If you have the data, though, you can go through this pathway to estimate the heat of vaporization change as a function of temperature. But the key thing overall, I don't care if we're talking about vapor-liquid equilibrium, if we're talking about just heating or depressurizing fluids, solid-liquid equilibrium, whatever the case is, the key thing to remember with these thermodynamic calculations is the reason why we choose these paths is for 2 reasons. One, we have an equation that allows us to calculate, for example, how do we change enthalpy as a function of pressure. We don't have an equation that tells us how to simultaneously calculate changes in pressure and temperature. Right? So we break it down into steps where we have an equation to calculate something and we have the data available. Right? So we can calculate pressure changes in enthalpy. We can calculate temperature changes in enthalpy. We have measured conditions where we know how the phase change enthalpy is. And so the reason why we're going through all of these seemingly arbitrary steps is because that's the way that we have equations and we have data. And that's the key thing to remember. The other thing is that everything is a function of everything else. So I cannot change the pressure of the system and have a phase change without changing the temperature of the system. If I change the pressure and I change the temperature, I change the enthalpy. Everything is a function of everything else. With the exception of ideal gases, there are no functions of pressure for the enthalpy on that one. That's sort of a nice simplification. All right, exam review on Wednesday, exam on Friday, normal office hours. So please go and attend if you have any questions, and see you on Wednesday.